Hello and welcome to Lessons Learned from In-Flight Machine Learning on board the OPSAT spacecraft for AI application in future EO missions. I'd like to give a big thanks to my colleagues Tanguy and Vladimir who went through a lot of effort to collect these lessons learned. OPSAT is a 3U CubeSat that was launched by the European Space Agency. It's equipped with a full set of sensors and actuators as well as devices that are made fully accessible to experimenters to run their experiments on board the spacecraft. Of particular interest is the 800 MHz compute capabilities as well as the available RAM from which the lessons learned are derived from. OPSAT introduced the apps paradigm in space, in which experimenters can easily develop, test, and deploy apps that run on board the spacecraft. The lessons learned come from developing and operating two apps, SmartCam and Orbit AI. Don't hesitate to reach out if you want some manuscripts to learn more about these apps and look at results. The first iteration of the SmartCam app was Classification 101, where we wanted to do onboard image classification with machine learning in order to help with downlink prioritization of images. We took advantage of the spacecraft's powerful computer to reuse frameworks that's been developed and matured for terrestrial application in edge and mobile devices. In this case, we selected Tensorflow Lite. What this means is that we can reuse the same architecture and training workflow developed for mobile devices, but to deploy apps in space for OPSAT. So anyone with experience in developing AI systems using TensorFlow and TensorFlow Lite for mobile devices can now do so with OPSAT in space. Subsequent iterations of the SmartCam app introduced new AI features. Recently, we've been experimenting with k-means clustering, so we have enough processing power on board the spacecraft to do image processing on a pixel-by-pixel basis of our high-definition image files. So for instance, here with k equals 2, we can achieve some level of cloud detection. With k equals 4, we can distinguish between land and sea. And with k equals 7, we can distinguish different depths of water and different depths of cloud. So none of this has been optimized. It's just very experimental and looks very promising. For our second app, the Orbit AI app, we wanted to demonstrate that in-flight model training was possible. To achieve this, we used online machine learning, specifically the algorithms listed here, and again, a demonstration of how we could leverage the compute capabilities we had on board. What's interesting about the Orbit AI app is that everything pertaining to training the models was developed as an independent service. So any app can connect to that service, send parameter data, that's training data, and select which algorithms to use to train what models in which dimension space. Developing and operating these two apps was an exciting preview to what the future holds, and here are some lessons learned from the experience. So number one, the availability of more powerful computers in new space and from COTS opens the door to technology that's been developed and matured for web and mobile applications. For instance, the SmartCam uses GeoJSON and GEOS to be spatially aware. GeoJSON was primarily developed for JavaScript for mobile applications. Orbit AI didn't develop any of the online learning algorithms from scratch. We forked it from GitHub. And the SmartCam uses image processing C headers in order to do pixel-by-pixel data processing. Lesson number two, when designing missions and systems for space segment, we still suffer a bit of tunnel vision from what's possible with the available compute capabilities. Now that higher processing power is becoming more readily available through COTS, it'd be really great to partner more with people who are familiar with web and mobile software engineering who can really bring in technology that's been matured in those fields that we can apply in space. Lesson number three is adopting a service-oriented mindset when designing software for spacecraft. OPSAT does a great job serving as a proof of concept for the CCSDS mobile standard, as well as operationalizing that standard. However, there's much more complexity we can achieve by looking and taking example from the web development world, particularly in approaches related to infrastructure as a service, software as a service, platform as a service, and microservices. This will allow us to take advantage of reusing services rather than always developing something from scratch. And lesson number 4 is designing missions that take advantage of the increasing capability of complex onboard data processing. For instance, pixel by pixel image processing like we did with the SmartCam, onboard training, machine learning like we did with Orbit AI, as well as taking advantage of multi-core processors. Last but not least, if you have an idea for an experiment to run on OPSAT, or even if you want to plug in Orbit AI and train your own model in Orbit, then great, apply to fly. It's easy and it's lots of fun. Thank you so much. Don't hesitate to reach out with questions, or if you want to have a look at these research papers, here are my contact information. And again, big thank you to my colleagues Tanguy and Vladimir.